is criminal to teach a man not to defend himself when he is the constant victim of brutal attacks.
It's called supercritical water, so it's the part of the phase diagram that you never see at school. You always see solid, liquid, gas, but there is a secret area that they never mention when you're doing GCSE chemistry. In your house you'll have gas lines or water lines in your radiators that run at maybe up to 4 bar pressure. This will run at 250 bar, 300 bar pressure, so it's quite a high pressure water system. And that's important because it runs at high temperatures as well. So it's a high temperature, high pressure system. It's like a kettle, but it's gone a bit far beyond what a kettle can do. It's a hydrothermal rig, so hydrothermal just means hot water. The real use for this system is we make nanoparticles in a hot water mixer. It all starts over here onto this side. So down here we've got 4 pumps. The bottom 2 pumps will pump liquids that have dissolved metal salts in them. So, you know, if people have ever made a crystal garden, they probably put copper sulfate in water, and you put a little thing in and the crystals grow on the string. The next thing that happens is that we'll take water through this pump here, and again this is all under pressure, so we'll go through this jacketed thing here. So all this is a heater, and it's a set of coils, and it's got a heater in it, and out the top it will be hot water. So in the bottom it goes in, it's cold water, and in the top it can come out as hot water at 400 degrees. So 400 degrees is significantly hotter than the average cup of tea, but if you've got it under pressure you can get to high temperatures. Once you've got the hot water flowing in here, it goes into the reactor. Now the reactor enables all the dissolved metal salt to come up and the hot fluid, the hot water, to come down, and it mixes inside the reactor. And this is the invention that we made. It's in here, so you can't really see anything because it's all in steel. And this is the reason why people are struggling to come up with a solution to the mixing problem, because you can't see inside steel. Nanoparticles form inside there, and then they're carried away in the water stream. I say water, but obviously at 400 degrees and 250 bar, it's not water and it's not gas either, it's not vapour, it's somewhere in between. It's called supercritical water, so it's the part of the phase diagram that you never see at school. You always see solid, liquid, gas, but there is a secret area that they never mention when you're doing GCSE chemistry and physics called supercritical region. Most fluids have it, and this is where it's no longer like a gas or a liquid, it's somewhere in between. Because what happens is you'll get nanoparticles formed when you have, it doesn't have to be a supercritical fluid, it could be just a superheated fluid. But water starts to dissociate, so it comes apart, everyone knows it's H2O, but then when it gets to these extreme conditions, it starts to dissociate. And when you get that dissociation, you get a unique environment where particles can nucleate. So these metal salts that are travelling up, these metal ions, can nucleate to form nanoparticles. So nanoparticles can maybe have 1,000 atoms in them, or more or less. But those are formed under supercritical or hydrothermal conditions, simply because of the dissociation of the material. This is a cooling system, so you might be able to see at the back you've got those transparent tubes, and that's got water flowing through it. So you have a tube with a hot fluid and an outer tube with a cold fluid flowing against it to cool it down. So then it's a lot cooler by the time it gets to that stage. At this point we can inject in organic material which maybe coat the outside of the particles and make them useful for, I don't know, sun creams or whatever we're doing with them, or printable inks. And after this stage we'll take the temperature down again, so there's another cooler here. And the final thing, which is this blue thing, is a regulator for the pressure. So the whole thing is under pressure, and it's all maintained under pressure by this spaceship looking thing there, and that just constricts the flow of the liquid out the final end of the tube. Stuff will flow out, different things to show you. This is nano rust. That's really useful. It's got all sorts of applications, from catalyst to, you can put it in lipstick and so on. It has obviously it has a very red colour. So that's iron oxide, hematite, so that's cobalt oxide, so that's a particular type of material that can be used as a catalyst in certain processes. And the final one, which is a whitish looking one, that's artificial bone, that's hydroxyapatite. So we can use this reactor to make a particular shape of artificial bone, which we think is going to be useful in the future. The applications that we're looking at here can be sort of chemical reactions, so can involve our chemistry colleagues, or they could be other applications in industry where maybe it's not a chemical reaction that you're going for. It might be that you're absorbing UV light, or that you're trying to make super hard composites or super hard body armor, or some other sort of physical phenomena that is useful in materials and so on. The particles here in this particular bottle are about 5 nanometers. Okay, and 5 nanometers means that you could fit thousands of these on a human hair in a row. Because they're so small. So a human hair maybe is a few microns in diameter, and one of these is 5 nanometers, so you can fit thousands of them. So if one of these particles is like a football, then maybe a human hair is maybe the size of a building. Okay, so you get some idea of the difference in scale. One of the things that process engineers are obsessed with is scale and making things commercial. So normally a research chemist will develop something, maybe like this on this scale, and then a process engineer will try and scale that up to be commercial. The other thing that we're obsessed with as chemical engineers is making things continuous. If you can have a system where things flow in, something happens, and things flow out, and it's more valuable, then that's the best way to commercialize a process. If you've got small batch pots, little containers, you do something, you stop the reaction, you take it out, it's very difficult to make that commercial, unless it's pharmaceuticals. So in our case, we've made this is a continuous system where material will flow in and then flow out. And if we're lucky, the kinetics of this process will allow us to scale it up quite easily. And that is actually what we've done. So I can show you the scale-up rig as well. What we decided to do before we formed the company is to make sure that we could take the lab-scale stuff that we're making and make the same kind of material at scale. So we actually built a rig. Now, it looks a complete mess at the moment. It works just the same as the small rig, but at a scale of about 30 times. The reason why it looks like this at the moment is that we've had to take all the guts out of the heating system to scale it up even further. So it'll be 180 times higher scale than the lab scale one. If you can manufacture at kilo per day scale, you potentially could service a lot of industrial markets. There's a lot of techniques for making the world's best nanomaterials at milligram scale, but they don't go beyond that. So if you've got applications where they're looking at needing a lot more material, you could never supply it. And so our investors were keen that we actually produced material on a bigger system. So we decided, again, before forming the company, to actually to build a bigger rig just to test it. So this was never designed for commercial production, although we use it for that now. It was designed just to prove the concept that it actually worked.
And it did it? It did the business, did it?
Oh yeah, and the funny thing was we ran it on the same day that we went for our final meeting with the investors. So that was an afternoon meeting in Leicester. And we were operating this at 11 o'clock the same day, so it was 11th hour, literally. We were operating this system. We made our first materials and then drove straight down to this meeting, so it couldn't have been tighter.